So today I'm going to be reviewing some of the concepts behind the nuclear bomb, as well as nuclear energy and different types of nuclear reactions and what occurs inside the reaction of the thermonuclear or fission or fusion bombs. This is a picture of a nuclear reactor. Nuclear energy is different than chemical energy in that the elements of reactions are converted into new elements, so not just changing into different compounds, but just new elements. This process involves not just electrons, but protons and neutrons as well, and in nuclear energy, neutrons are especially really valuable in reactions. They're used to power chain reactions that drive explosions that we associate nuclear energy with. Also, unlike chemical reactions, they're not affected by things like temperature, pressure, volume, things like that, or don't need the additional of catalysts, and they produce extremely large amounts of energy, whereas chemical reactions are more small scale. So there's a lot of information on the slide, but these are the major points that I found that highlight the differences between fusion and fission reactions. So one of the major differences I found was that fission reactions divide a heavy nucleus into smaller nuclei, and the neutrons release large amount of energy, whereas fusion reactions, small nuclei are condensed and energy is released in the process. Fission, the most well-known fission bomb is the Hiroshima bombing in Tokyo. This was highly exothermic, and for this reaction to occur, TNT is used as an explosive to change the critical mass in the atomic bomb, which is primarily made up of uranium-235. These types of bombs produce a lot of radioactive nuclear waste, which is why they're really harmful to society. The effects of the half-lives of some of the chemicals used in these bombs have long-lasting effects on the area that they impact and the people. And this, in general, therefore, is not favorable for energy because of the long half-lives of the isotopes. 3 Mile Island is actually, we read about it in the textbook, and that's something that's actually 20 miles north of where I live, and it's something that I have someone in my family that works at a nuclear reactor, and so it was interesting to learn about that and kind of how the science of the nuclear energy works there, and about the large waste disposal problem for nuclear energy in general. But anyways, going back to fusion, which is why I'm presenting this. So fusion, it occurs between hydrogen and helium atoms, and so these atoms, hydrogen atoms, are condensed into helium atoms, and this takes place organically at the surface of the sun a lot because of the high temperatures that are needed, and because temperatures are so high required to produce these reactions, science hasn't caught up to figure out a way to safely produce energy from these reactions. But if it could be figured out, it would be really beneficial because there's little radioactive waste in these reactions, and hydrogen and helium are readily available always, so there wouldn't be a problem with resources. So fusion occurs in hydrogen or thermonuclear bombs, which is what we'd be looking at. And unlike the fission reactions, no critical mass is needed for this bomb. It's only limited by the amount of explosives present. However, fission is needed before fusion occurs. So this is a slide that I found that I thought, it's from our textbook, and I like the way it presents the two reactions. I think it's visually easy to understand. So here we would have the fission reaction and the fusion. So there's a lot that happens inside the thermonuclear bombs, and like I mentioned, so first, the first reaction that would have to occur would be a fission reaction, nuclear fission reaction, and this reaction produces the high heat that is needed for the hydrogen fusion to occur. Fission also produces X-rays and an abundance of neutrons that will also contribute to the fusion part of the reaction. Neutrons from the fission rod combine to produce, so the reaction goes to lithium, titrillium. I have a slide here with the actual tritium from lithium ditride. Sorry, I can't pronounce these very well. So this is the reaction that would occur inside the fusion bomb. Here it shows that they use uranium-238 that supplies the neutrons from the fission reaction to fissionable material. So going back to this part. The second part reaction, the hydrogen fusion would occur. The hydrogen fusion cycle involves 4 hydrogen protons and 2 electrons and yields a helium nucleus. This process occurs in 3 steps. So I have this diagram here. So during the hydrogen fusion cycle, hydrogen is fused into deuterium, and so 2 protons collide, and then they turn into a neutron and another proton, and they form a heavier molecule here, and then comes off the helium particle and then an extra fast electron. So as you can see, the hydrogens fuse and then we get the helium. And here's an example I found of how the bomb would be set up. So there was a lot to learn in this chapter, but overall the reaction that occurs is the hydrogen is squeezed together at really high temperatures and high pressure fuses the hydrogen atoms into helium. So overall I think this is an extremely unique process. It's exciting to see, although it's somewhat anxiety inducing, how these reactions can be used. It's exciting to see how we can possibly figure out a way to safely utilize this into energy, that a safe energy source in the future. I know there are nuclear reactors now, but figuring out a way to handle waste and everything. Personally, I work in medicine. I work actually really closely with nuclear medicine. They perform a lot of tests for our patients using isotopes and tracers and doing the PET scan. So there are a lot of benefits to nuclear medicine and nuclear reactions. So that's it.